So in this lesson, it's talking about mixtures. So in a previous lesson, we talked about how a pure substance is an element or a compound. A mixture is made up of more than one pure substance, and that's as far as they get in AP chemistry. They don't talk about types of mixtures. It's just a mixture is just something made up of more than one pure substance. So we need to review really quick the concept of a diatomic element because we need to know what that means. And we also need to just remember which elements are diatomic. So a diatomic element, the prefix di in chemistry means two. So a diatomic element is an element that bonds to itself for stability. So right now you're breathing in oxygen. It is not just O. It is not an atom of oxygen. It is O2 because they can covalently bond and become stable. And they have that subscript of 2, and that is what a diatomic element is. So it's a single element, but it has 2 of them. And so your diatomic elements, I told you guys to memorize based on where they're at on the periodic table. A lot of times I tell you that it is a hockey stick and a puck. And so the hockey stick is starting with nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are your ones that are the hockey stick. And then the puck is hydrogen. Those are the only elements on the periodic table that are diatomic. There are some elements that bond in more ways covalently, but we're not worried about that. AP loves giving these particle diagrams. You're going to see a million particle diagrams. You're going to draw a million particle diagrams. Because if you understand what's happening at the molecular or atomic level in chemistry, then it shows them that you really, really understand what's going on in chemistry. So we are asked to either identify from a picture or draw these particle diagrams. In this one, it gives us 4 different things, and we need to try to guess is this a mixture or is it a pure substance based on the information given. So at the top of this picture, it tells us an atom of X is the black ones, and an atom of Z are the hollow white circles. And then we have to look at how they are combined or if they're individual atoms. So in this first picture, this is considered to be a mixture because it is going to have, let me go ahead and get my pen ready so I can write. So A is a mixture made up of the atom X. It is by itself. And then the other thing is Z, but it's not an atom of Z. They are connected. And so the way that we would write it is Z with a subscript of 2. Mixture B, if we look at those, in this one, all the black dots are not connected, meaning that it's an individual element. These 2 are connected, and they are bonded. It is covalent, but they're still considered to be a single element because they're just one substance by itself. Over here, I have a compound. I have 1 black dot and 2 white dots, and it is consistently the same pattern all the way throughout. So B is a pure substance. It is a compound. It's made up of 1 X and 2 Z's. So the chemical formula is XZ subscript 2. C is all the same. It is the same thing over and over, same pattern. So this one is going to be a pure substance because it is only containing one type of thing. It is containing my element Z bonded to itself. So all that's in there is just the diatomic version of Z. And then picture D has these black dots, but it also has these compounds. So this one is going to be considered a mixture because it does not have only one substance. It has these black dots, which is X by itself. And then it has that compound we saw in picture B. And so then it also has XZ squared. In mixtures, these things are not chemically combined. They are just sitting in that container together. Pure substances are all uniform and have just one type of substance throughout it. So sometimes you're going to be asked to identify things based on these particle diagrams. So start getting comfy with seeing those, and then later we actually draw them. So these are more likely the type of problems you're going to see is where you are asked to calculate the percent of a mixture. So in my class, you guys did a separating a mixture with sand, salt, and iron filings. And to figure out the percent of each part of that composition, we took the mass of each individual thing over the total mass times 100. And that total mass percentage would then, if we added all those things together, would end up adding up to 100%. We also did this when we did the popcorn lab and the gum lab, where you guys calculated out how much sugar is in gum and how much water is in popcorn. In these, you're going to have chemical formulas, and we're going to have to do a whole bunch of mole conversions in order to be able to get to this final equation. So this says that overall, the total sample is 2.4 grams. That's my total mass of my mixture. It says of a mixture of calcium chloride and sodium chloride is found to only have 0.12 grams of sodium. What's the percent of this sample in sodium chloride? So my first problem is I only have grams of sodium and I need grams of NaCl. So we're going to have to do several conversions before we can actually get to using this final equation. This is the big picture equation, but we got to do a bunch of mole conversions before I can get there. And so I'm going to start with 0.12 grams of Na. In any of these problems, the first point is to get it into moles. Moles is the common unit in chemistry, so I got to get it into moles. So my first thing I'm going to do is cancel my grams of Na. This is going to come from the periodic table, and on your periodic table, it's 22.99 grams of Na to 1 mole of Na. So now I'm into moles of Na, but again, my big picture item is I got to get to NaCl. So we're going to do like we did before, where we are converting. If I'm doing 1 molecule of something, I can also do mole of something. And so I'm going to do 1 mole of Na is equal to 1 mole of NaCl, because they have equal amount of each of those based on the chemical formula, because NaCl doesn't have any subscripts. So it's 1 mole of each. Then I'm going to go over here and convert to grams of NaCl. So this sort of looks like a stoichiometric calculation, but we're not changing substances. We're staying within the same compound, but it's the same concept that we're using that conversion. So then on top, I'm going to have grams of NaCl. This number comes from the periodic table. So I'm going to get the mass of my 1 Na, which I already said was 22.99, plus 1 Cl, which is 35.45. And that gives me 58.44. I'm going to multiply and divide all these things together to get that final amount of my grams of NaCl. So mathematically, I'm going to do 0.12 times 1 divided by 22.99 times 1 divided by 1 times 58.44 times 1. Again, there's lots of right ways you can put this in the calculator, but there's also wrong ways because your calculator works off of order of operations. So if you do not get the same answer that I am getting, it's because you're plugging into your calculator wrong. I need to round to sig figs. This only has 2 sig figs. My calculator gives me 0.305, which is going to round to 0.31 grams of NaCl. Now that I actually know how many grams of NaCl I have in this sample, then I can use my equation. So I need the mass of the substance over the total mass of the mixture times 100 to get my mass percentage, because it says what percent of this sample is NaCl. So I'm going to divide this by 2.4 grams of the sample times 100. So I'm going to do 0.31 divided by 2.4. Again, be real careful when you're plugging these in your calculator. Make sure that you're using the right order of operations. Whenever I multiply it by 100, it gives me 12.9. I need 2 sig figs, so that's going to round up to 13% of NaCl. So then, once we have that calculation, we can go on to another one that's similar now that you've seen the format once. So let's do it again with a different example. This one says a 5-gram sample of a mixture of CaCO3 and SiO2 contains 1.5 grams of Ca. What is the percent of CaCO3 in this mixture? So first thing is I've got to get to grams of my CaCO3 before I can use that percent equation. So I'm going to start with my given. This is my total sample, so I don't use it yet. So I'm going to use the 1.5 grams of Ca. I'm going to divide by the mass of calcium, which is 40.08, to 1 mole of Ca times 1 mole of Ca. If I look at the formula, again, there's 1 Ca in it, so it is equal to 1 mole of CaCO3. And then I'm going to have 1 mole of CaCO3 to the grams of CaCO3. I'm going to add up my 1 calcium, so 40.08, plus 1 carbon, 12.01, plus 3 oxygen, so 16 times 3. And that gives me 100.09. Then again, I'm going to mathematically calculate it out. So I'm going to do 1.5 divided by 40.08 times 100.09. And I need to round to 2 sig figs. So it ends up being 3.74, which will round to 3.7 grams of CaCO3 divided by my total sample, which is 5.0 grams of my sample, times 100. I need 2 sig figs because of 3.7 and 5.0, and it comes out to exactly 74, so 74% of CaCO3. So again, these problems are not terribly difficult, but it's a lot of conversions. That is all chemistry is a lot of conversions. Some sort of mole conversion happens almost every single lesson. So this is an example of how they might ask this question on an AP test. So it says the mass percent of carbon in pure glucose C6H12O6 is 40%. A chemist analyzes an impure sample of glucose and determines that the mass percent of carbon is 38.2%. Which of the following impurities could account for the low mass percent of carbon in the sample? So this is going to challenge your understanding of what mass percent means. And so if I were just asked to do the percent composition of this chemical formula, then I would do the carbon divided by the total mass, and it'd give me the percent by each element. We've already done that in a previous lesson. But this means that it's an impure sample means it contains something else. And so if it contains something else, but it had a lower percent of carbon, that means the something else it contained doesn't have carbon. That's what this means. Because if it had carbon in the other impurity within this sample, then my percent would be greater than 40%. But my percent is lower than 40%. And so if I look at these formulas, I have H2O, C5H10O5, C6H12O6, and C12H22O11. Well, all of these have carbon, so they cannot be the impurity. And so the impurity is going to be A, would be our correct answer, that we would have H2O is our impurity because it's the only one that does not have carbon, that would not add to the mass percent of carbon in that sample. So some of these questions are going to require math. Some are going to just require thinking about the problem.